Hi, RDBury here. Last time I said I was going to do cubic bases in this episode, but I realized that I really can't do that without doing a little bit of an introduction to something called PV numbers. Um, so I'm going to do that this time, and maybe next time we'll get to the cubic bases, or the cubic irrational bases. Um, so let's get started with that. What I've done here is I've set up a spreadsheet with now what it is you take a quadratic polynomial. In this case, the coefficients are 1, -1, and -1. So the polynomial is x squared minus x minus 1. And that's the polynomial for the golden ratio. Basically, the golden ratio squared is equal to itself plus 1. And in this cell here, I've put in the quadratic formula to solve that equation. And then all the way down here are all the powers of that solution. So here is the phi, and then here's phi squared, phi cubed, etc. This is phi to the 0, which is 1. Now, one thing you're going to notice here, or hopefully, is that as you get further and further down this list, these numbers get closer and closer to an integer or a whole number. They're not quite equal to a whole number, but they get closer and closer to one. And what you can do is you can work out what that number would be if this works, or when this works. For example, here it says 2206.9, which is almost 2207, and that's what is put here. These, in this case, these are the Lucas numbers related to the Fibonacci numbers because they follow the same rule. You add the previous two, like here you add 7 and 11 to get the current one, and then add 11 and 18 to get 29. They're similar to the Fibonacci numbers, but you start with 2 and then 1. And it turns out, as the rule is here, that these powers of phi just get closer and closer to these Lucas numbers. In fact, as you get down here, you can't even, it's beyond the limit of the display here. It's already down to 6 digits of accuracy, or actually 12 digits of accuracy. So the other thing I've done here is I've compared these two numbers, this column and this column. I've subtracted, and that gives me this value here, and I'm sorry, it gives me the value in this column. So for example, this difference is 0.09. That's the difference between this value and 11. And this chart here just graphs those values. And you can see that they get, as you get further and further along here, these numbers rapidly approach 0. Now, with the bases that we've done so far, with the quadratic ones, that will be the pattern, that the sequence of powers will approach this sequence, and the differences will get closer and closer to 0. So the magic formulas for the next few ones, quadratic bases are 1, -2, and 1. So x squared equals 2x plus 1. And you see you get the same pattern. It actually gets closer to 0 even faster than before. The next one is actually phi squared, and the magic formula for that is x cubed, or x squared equals 3x minus 1. This approaches 0, but in this case it's always stays on one side of the 0. It's always going to be slightly less than the number I get here, but it still approaches the number or these numbers very quickly. And finally, the other one we did was the magic formula was -2 and -2, or x squared equals 2x plus 2. And this one doesn't approach 0 quite as fast as the other ones, but it's still fairly obvious that it's getting down there fairly quickly. And these curves kind of always have the same shape. It's an exponential shape. It's called exponential decay, I guess. So that's the case when the number works as a base that where the which works the way we want it to. In other words, the whole numbers come out with a finite expression. The rational numbers come out with a periodic expression, and we can see that if that's not the case, I think in the first episode I tried the square root of 2. In that case, the magic formula is x squared equals 2. And in that case, you can see it doesn't approach 0. In fact, it blows up and goes to, or it becomes larger and larger. And that's because in our in this is the sequence of numbers that we expect it to do. This just kind of goes back and forth between 0 and some power of 2. So it's not going to be, it's not going to look like this a sequence of powers at all. And sure enough, when we tried the square root of 2 as a base, it didn't work the way we wanted it to. We got just sort of random stuff as soon as we got to trying to do 3 base square root of 2. And other numbers, the ones that work turn out to be exactly the numbers where this, you see the pattern where the differences here approach 0, and not only do they approach 0, but they approach 0 relatively rapidly. Now there's a name for numbers like that, and they're called PV numbers. They're named after 2 mathematicians. The first one is a French mathematician. I'll give you the Google pronunciation of that because my French pronunciation is not perfect.
Charles Pizot.
Okay, Charles Pizot. It's my best attempt. The second person they're named after is, and I'll give you the Google approximation of that. He's a Tamil mathematician.
Irukkannapuram Vijayaraghavan.
Okay. So my attempt on that is I'm not even going to do the first name, but Vijayaraghavan. So I think for kind of obvious reasons, I guess the Tamils like to have or like to give themselves longish names. So what I'd like to call them is our PV numbers. They're also called piezo numbers, or sometimes other things. Actually, it turns out neither one of these guys actually discovered these things. That was a mathematician named Axel Thue, Thue. For some reason, his name isn't attached to that, but that's what happens in mathematics a lot. So anyway, that's the name PV numbers, and they've been around. They've been studied for a long time. They've been in contexts that don't have anything to do with what we're talking about at the moment. Get back to where I was here. There we go. So so anyway, that's the thing we need to talk about, because the condition that a number is a PV number turns out to be exactly, or nearly exactly, the what we need need to look for the number to be usable as a base like this in the way we want. So let's go to the cubic equations. Now, I did not program in the cubic equation into this, so I'm using basically a numerical approximation here instead. Here is a cubic equation, and this turns out to be a PV number, and you get this in general that it is kind of approaching zero. It's actually doing it fairly slowly, but the problem is it doesn't just alternate back and forth or just stay positive or negative. It does some interesting things, and with different cubic equations you get different types of behavior, but with a PV number it always has the same kind of feature where it always approaches zero eventually here. So let's, as a simpler example, I'm going to do the Fibonacci constant. So instead of just x squared equals x plus 1, it's x cubed equals x squared plus x plus 1. And for that one, the sequence you want is the rule is you add the previous three numbers. So 7 is 3 plus 1 plus 3. 11 is 7 plus 3 plus 1, etc. That tells you everything except how to start. It turns out for cubic equations, you always want to start with 3. The next two, you need to, you can work out formulas for what they do. You can read them hopefully off the screen here. This is basically just the negative of the coefficient there. And this is the coefficient there squared minus twice the next coefficient. And you can do similar types of things for fourth degree polynomials, etc. But this is all I'm going to do for the moment, at least. Now, to get the constant here, or what the actual solution of that is, well, I can use the property that these numbers are supposed to be approaching the numbers in this sequence to adjust this value to get more and more accuracy out of it. So first of all, I know this is closer to 2 than it is to 3, so I'm going to start out with 2 there. Right. These numbers are all too big compared to these. In fact, the difference here is 11. So these powers are too big, so I'm going to just decrease these a little bit. So let's try 1.9. Still too big. 3.61 is bigger than 3, so let's try 1.8 instead. Now I've gotten too small. So I need to increase that a little bit. Now what I've done with this column, once I've gotten in the right neighborhood, this basically applies Newton's method. If you remember that from calculus, if you've had it, you can use Newton's method to solve an equation. So this basically says what do I have to add to this number for its 20th power to be equal to this number? And it turns out if I do that, and I keep on doing that kind of thing repeatedly, so I'm going to add that difference there, and hopefully it'll get closer and closer, to the solution. So I'll keep on adding that. Now eventually, now the numbers are within about a millionth. And now they're within, I guess, about a billionth. Now I'm going down to the very end because I want to make sure that this is accurate down to the last entry there. And I'll add it there. So just a small difference now. And now the numbers are so close that that my spreadsheet can't tell the difference. Occasionally I get some rounding error, but that's what that's as close as it's going to get within the accuracy of the spreadsheet. And now you see that you get the pattern that we were expecting here. These numbers here, they start out, the differences are fairly large. Here it's 3, for example. Oh, I'm sorry, no. Here the difference is 0.38. Here the difference is 0.7. So they do start out large, but they get smaller and smaller fairly rapidly, and until eventually you get to something like this, where the difference is about 100th. Here the difference is about 1,000th, and so on. So this has, again, it kind of doesn't do a kind of regular up and down motion, but there's some like randomness here, or chaos in terms of how far the number is from what it's supposed to be, but it does still approach 0 fairly rapidly. So what I've done is I've kind of done that for to find all the cubic PV numbers up to I think I went as far as 4. So it turns out with quadratic PV numbers, there's you can figure out the number between any two whole numbers. For example, between 1 and 2, there's only phi. So there's 1. Between 2 and 3, there's 3. And that's why we did an episode with three irrational bases. It was exactly those same 3. Between the next two whole numbers, there are 5, and then it goes 7, and then 9, etc. So that pattern is fairly easy to see. With cubics, and I've done the list here. Let's scroll up to the top here. With cubics, there are 4 between 1 and 2. This is the so-called plastic number. This is the Fibonacci constant that we just did. this is kind of a variation on the Fibonacci constant where you, instead of looking at the previous three, you just look at the previous one and then skip one and then do another, then do that one. So, and then there's this one here, which is actually the so-called plastic number squared. This number is this squared. Now, there's not a coincidence there that we keep on seeing powers here, because it turns out that any power of a PV number is also a PV number. Now, I just want to talk a little bit about how you can find these. Turns out that this is a great way of finding the actual value of one, but in terms of finding the coefficients you're starting out with, that's a little bit more tricky. And what we needed for the quadratic, what the actual condition for a PV number is that if you have the positive root, that's going to be your number, and every other solution to that equation has to be between 0 and 1. I'm sorry, it has to be between -1 and 1. So for example, for the golden ratio, this is our main root, but the other root is -0.618. In fact, it's equal to just the negative of the fractional part of that. So the same thing happens with the silver ratio. In this case, the other solution is -0.414. And it works similarly for the other ones. So for a quadratic PV number, what you want is that the number is that the other solution, it's a quadratic equation, so there's going to be two solutions. And other than the ones you want, the solution is always between -1 and 1. Now for a cubic number, that's sort of what you want. You want there to be no other solutions greater than 1 or less than -1. But the problem here is you might have two imaginary solutions. I don't want to get too much into imaginary numbers here, but the upshot here is that if it does have imaginary numbers, they can't be any further, or if it does have imaginary solutions, they can't be any further than 1 from 0. And you can use that to narrow down what coefficients you look at there. So anyway, so what I've done, these are the 4 cubic PV numbers between 1 and 2. These are the 16 PV numbers between 2 and 3. And these are the let's see, these are the 36 PV numbers between 3 and 4. Now the pattern there is, this is 2 squared, this is 4 squared, 4 squared numbers, and there are 6 squared numbers. So 4, 16, 36. Between 4 and 5, there are going to be 4 squared numbers, or 64 of these things. So you can see they get to be really, they get this they get closer and closer together the higher you go. Now, what is this? What are these mysterious colors over here? Well, what I've done is, for some of these, you can just read off what the rule for the digits is. For example, this one, the rule for the digits is you can't have any more than 3 ones. You can't have three ones in a row. It has to be 0 or 1, and you can't have you can't have 3 ones in a row. And the way you can read that is that you look at the negatives of these numbers here. So here I get 1, 1, 1. And if your sequence of digits has any part that is greater than those, and by greater I mean in dictionary order or lexicographic order, then you can do a carry, and that sequence isn't allowed. So this basically says, since I have a 1, 1, 1 here, that I can't have 1, 1, 1 in any digit sequence for that base. In other words, I can only have at most 2 ones. This one here says I can't have a 1, 0, 1, and also a 1, 1 would be greater than 1, 0, 1 in dictionary order. So I can't have that either, or I can't have that either. And so the rule for this one is I must have at least 2 zeros after a 1. If I had less than 2 zeros, I'd have a 1, 0, 1 or a 1, 1, and then I could do a carry. Now for this one, the rule is it kind of skips a bit, but it says that I must have at least 4 zeros after every 1. You'd think there'd be something in between there, like no, there's one where the rule is you can't have 3 zeros, but that turns out to be a fourth degree base. It does work. It is a PV number, but it's a higher degree. And here, this turns out there's some additional factors in there that we can eliminate, and we just get this cubic, and that number gives us the PV number. This is the smallest PV number of any base, by the way. Pretty sure it's the only one that's less than the square root of 2, and we'll get into that in the next episode a little bit. That will cause an interesting thing to happen in there. So, and I've color coded these according to the length of the rule. So the green ones have the most basic rule. These greenish blue ones have like the next level of rule. So they're in this one you can have if you have 2 ones in a row, then you must have at least 2 zeros in a row. So it gets a little bit more complicated. With these red ones, that's even longer type of rule. Then there's the orange ones. These have actually infinite length. So this says if you have a 2, then it must be followed by a 0. And it can't be followed by a 0, 2, and it can't be followed by a 0, 1, 2, or anything along those lines forever. So it has to start with a 0 and then have either zeros or ones, and the first sequence of ones must end with a 0, basically. So, and this one, you get a similar type of thing. This is a little bit slightly different because in this one, the rule kind of alternates between zeros and ones. And the way you generate these things is you basically write the number in terms of itself, base in its own base. So, for example, For this number, the number is equal to 1.01 in its own base. And when you work that out and put it in terms of a formula, you get something like that. For this one, you get, in terms of its own base, the number is equal to 2.0101 repeating. And so that one's a little bit odd in that you didn't get this well, you kind of got this phenomenon in the quadratic equation or quadratic bases with pi squared had actually its formula would be 1, -2, and then -1s, continuing like that. But this is even more complicated in that in this case you have you have a period of 2 there. And you can kind of, once you have the degree, then you can kind of divide this up into families according to this color code here. It gets a bit tricky because there's some real oddballs here that, well, they do have families. They're kind of in an infinite family of families. So I've just called those gray. You get more of those when you look between 3 and 4, and they just kind of defy all logic there. So those are the cubic PV numbers. You can continue on and do quartic PV numbers. The problem with that, though, is that with quartics you also get something called Salem numbers. Now, Salem numbers are similar to PV numbers, except they're kind of edge cases. And when you do when you write things out with a Salem number as a base, things get really, really odd, and it's kind of hard to predict or hard to prove. I mean, you can kind of see patterns, but I don't know exactly the proof for anything that I've seen with them. So I just sort of avoid that whole issue by just sticking to degree 3 or less. And we see enough interesting phenomenon with the degree 3 PV numbers by themselves. So I'm going to cover that next time. I'm going to just look at these first 20 bases, so up to but not including 3 here, and just look at the numbers from 1 to 100 in each of these bases to see what we get. And there are some surprises in there. I won't say everything has its own unique set of surprises, but there are some oddballs that do have some surprising things happen. So I hope you will join me for that episode, and until then, bye.